Welcome back. This is our second video on exponential growth, and we'll finish one more example. I just want to, I actually made a mistake on the last video, so I want to correct that mistake before we continue. First of all, here where it says population after t years, this isn't correct. What it should say is it's the population after time t, because t could actually, remember I did mention that time could be in different units. I mean, the rabbits were in months. It could be in definitely different units. So you definitely want to adjust that, maybe fix that, because it's not in years. It could be in any unit as long as you're consistent with it. Okay, let's go ahead and look at an example. All right, so between 2000 and 2010, the population of Iowa City grew from 62,200 to 67,900. Assuming exponential growth, let's find the year the population broke the 60,000 mark, the year the population will exceed 70,000, and the population in 2025. So, first things first, the model. The model we know is we have this population. It's a function of time. We don't have to write this, but it is a function of time. There will be an initial population, which we actually know, 62,200. And that'll be e to the r times t, where r is the growth rate and t would be the time, and the time will be in years. But just to kind of gather the information in a way that's useful, notice that in the year 2000, this is sort of when we start measuring, year 2000. So this is the year we start measuring. We'll call this time equals 0. And the population here was P was 62,200. And since it's the initial population, I'm going to actually say P naught. In the year 2010, just 4 years ago, that's when time was 10, because that's 10 years after the year 2000. Well, there the population is 67,900. Now, in our model, we have that P of t then is equal to 62,200. But in order to use it, remember, depends on time, I need to know the rate. And so that was the purpose of the first example, was to get you to think, well, how do I find rate? Well, we just need some information. And the information that's going to be useful to find the rate is actually here. When time is t, P is 67,900, which means in this model, I can replace the P of t with 67,900, and I can replace the t with 10. And so when I write this out, I'll get that 67,900 is when I plug in to the model 10. All right, well now we need to find r, we need the growth rate, otherwise we can't predict anything. So here, now what we do is we solve for r, and we know how to do this. We know that we can divide 62,200 on both sides. These cancel. And let me move this up a little bit. And then it's just a matter of continuing the algebra. Here on the left, the number is not nice. It's 1.09 and a bunch of other stuff. Again, I don't round, so I would suggest you not round until the very end. And you get e to the 10r. And then what we do is we take the natural log of both sides. So the natural log of 1.09 and the other stuff that I don't have here. And here the natural log of e to the 10r. Remember, all we're doing is taking this function and putting these inputs in. The nice thing on the left is that you'll get just 10r. And here you'll get the natural log of 1.09, ... And then to solve, all I have to do is divide by 10. Divide by 10. And so I get that r is approximately 0.0087681035, or 0.879, or 877 ... And so again, I don't round until the very end, but I'm going to keep this like this. But for shorthand, so this is part A. This is the answer to part A. We haven't found part A yet. We need this. Now we can go ahead and answer part A. Part A says, what's the year the population broke 60,000? The year, so that means they're asking us for time. So our model, now, we know what our model is. Our model is 62,200. E to the r, which is this number, so I'm going to go 0.0087 ... times t. Okay, that's our model. And they're asking us in the first question is, they want the year where the population is 60,000. So what they're telling us is This is 60,000. Find the year. Find t. And so when we set this up, we said 60,000 is equal to 62,200. E to this weird number, t. Well, we know what to do again. It's exactly the same steps we just did right now. We divide both sides by 62,200. This cancels, and the left-hand side actually is close to 0.967 and some other. Again, I don't round yet, but I wanted to round for this. Here I get e to the 0.0087 t with some other stuff times t. We know we take the natural log of both sides. Notice that I skipped a step. When I take the natural log on the left, I already know it's going to cancel the e. And so when I solve for t, you divide both sides, we get that t is approximately negative 3.7. That's a weird answer. We've never really talked about negatives in models, but think about it. If the model is correct, what it's telling me is that if the initial time was 2000, if t is negative 3.7, that means it's maybe more than 3 years before. So sometime in 1996. So to answer this question, the year the population broke 2000, well, the population broke 2000, sorry, not 2000, 60,000 in 1996. Well, that kind of makes sense, right? Because in the year 2000, we have 62,000. So it must have been before. It's been growing, so it must be before. And 1996 seems like a reasonable answer. I don't know if it's correct, but it's at least a reasonable answer. All right, so let me squeeze this down. Let me move this over here. We've answered part A. So now let's go ahead and try B. The year the population will be 70,000. The setup's the same, so I'm not going to go through all of it. I'm going to actually let you guys, because it's actually exactly the same. It is 70,000. And we set it equal to 62,200 e to the rt, where r is this weird number. And then after you do all the work, t should be about 13.4 years. And so sometime in the year 2013, so in 2013, somewhere in there, the population will exceed 70,000. I'm not sure if it does. I try to find. You might want to look up that information online, see if it's true. If in 2013 it reached 70,000, I would assume that it's probably true. It's probably reasonable. And then finally, you want to predict the population in 2025. So in 2025, that's 25 years after 2000. That means t is 25. And so all this problem is telling you to do is plug in 25 into our model. And so we get that 62,200 e to this weird number, again that I'm not rounding, that's the r, the growth rate, times 25. And then after I work that out, this is just plug it in your calculator. If you're having trouble with that, please ask me. But after that, it turns out that in 2025, Iowa City should have about 77,195. I won't be here. I don't know if any of you, but maybe you can tell me later if this is true. All right. This actually concludes. This should help you with one of the problems in your homework. So good luck.